Good morning, students. The next video, this video includes the estimation of theory of estimation part 3. This video includes methods of estimation, methods of estimation. Commonly used methods are maximum likelihood estimation, method of moments, method of least squares. Based on our curriculum, these three are very, very important for the examination point of view. First one, two are very, very important. So topics for the regional-wide and nationwide examinations. Method of least squares. Third, method of estimation is also very important for the regional-wide and nationwide examination point of view. Starting with maximum likelihood estimation. The method of maximum likelihood, parameter or estimator, maximum likelihood parameter was initially formulated by Gauss, C.F. Gauss, but a general method of estimation was given by R.A. Fisher. Before taking the MLE, first of all, you have to know the definition of likelihood function. What is likelihood function? Simply, we can say that product of the marginal PDFs or product of the marginal probability mass functions gives the likelihood function. The product of the marginals gives joint PDF or joint probability mass function. Directly, the joint PDF is called likelihood function. Let x1, x2, xn be a random sample drawn from the population. Population has probability density function f of x comma theta. Then the likelihood function of the sample values x1, x2, xn, usually denoted by capital L, is their joint PDF is given by f of x1, x2, xn given theta is equal to f of x1 into theta, f of x2 into theta, f of xn theta. So f of x1 comma theta, f of x2 comma theta, f of xn comma theta. Xi's are IIDs. So f of x1 comma theta is the marginal PDF or probability mass function of random variable, either discrete random variable or continuous random variable. For x is discrete random variable, f of x1 comma theta is the marginal probability mass function of x1. Here x1, x2, here x is a continuous random variable. So now, in this case, we consider the marginal PDF of x1. Marginal PDF of x1. Parameter is theta. But parameters are same here. Second one also marginal PDF of x1, x2. Last one, marginal PDF of xn. Product of the marginal PDFs gives joint function. So it is called denoted by L. This is L. L is equal to phi I is equal to 1 to n f of xi comma theta. Here, for example, x follows Poisson distribution, xi follows Poisson. The random sample drawn from this one, I is equal to 1 to n. I is equal to 1 to n. How prepare the likelihood function? So the probability mass function P of x equal to e power minus lambda power xi by xi factorial. Xi factorial P of xi. Now likelihood function is equal to pi I is equal to 1 to n samples are drawn, e power minus lambda power xi by xi factorial. Now here is e power minus lambda is constant. So pi means product here n times e power minus n lambda power summation xi base equal powers added by pi xi factorial. This is the likelihood function. It's a radical function. So in further, so simplifications, we have to take the logarithms. Easily we can simplify this likelihood function. So this is the process to write the likelihood function of the given distributions. Now here, procedure of MLE. Here is briefly, first of all, you have to find out the likelihood function. Here we have to find the maximum likelihood function. For what value of theta, the L is maximum. The theta is called the MLE. For what value of theta, L is maximum. The theta is called the MLE of the, so MLE of parameter. Maximum likelihood estimator of the parameter, unknown population parameter. Theta belongs to parametric space. We must maximize the likelihood function with respect to theta, a variable as such that likelihood function will be maximum when. Here we have to use the principle of maxima minima conditions. The principle of maximum minima is a mathematical technique. Mathematical technique. It's a mathematical concept. First of all, first to find out the, here is the mathematical principle of maximum minima is, first of all, here is find out f dash x. Here is equating to 0 and solve it. So x is equal to x1, x2. So x maybe has at least one solution. Third one, find out f double dash x. F double dash x is less than 0 at any one at any point of x here. Suppose at x equal to x1, f double dash x less than 0. F of x has maximum. F of x has maximum at x equal to x1. This is a procedure, principle of maximum minimum. Similarly, you have to apply the same technique in this case also. Here we have to find out the maximum L. For what value of theta maximum L? That theta is called MLE. So here is a likelihood function after construction is over. Construction of likelihood function is over. Immediately you have to find out the differentiation of L with respect to theta and equating to 0 and solve it. Second derivative d square L by d theta square, definitely less than 0 at this point here. So d square L by d theta square less than 0 at any point, any value of theta here. That theta is called the MLE of this one. Theta is the estimate obtained from the equation dl by differentiation of L by d theta is equal to 0. But L is a radical function. L is a product of the marginals. So now the differentiation is very typical. So L is a PDF, is a probability value. L must be greater than 0. In this case, here we have to, our convenience. So we have to apply the logarithmic concept. So take log L. So L is maximum when log L is maximum. So now here we can apply the logarithmic function. So our convenience for easy differentiation to get the requirements. So instead of L, we should take log L. Replacing L by log L, we get the values of likelihood estimator theta cap, a solution of the equation. In this case, first step is after applying the logarithmic function to the L, differentiate log L with respect to theta equal to 0 and solve it. We get different values of theta. Substitute theta values in the second derivative, which theta value gives less than 0, so that log L is maximum at that point here. So therefore, theta value maximize this L, the theta is called the maximum likelihood estimator of the population parameter. So 1 and 2, point 1, point 2 are usually referred to as likelihood equations for estimating the parameters. This is the process here. This is a procedure. So I am giving the one example. Using this procedure, easily we can find out the MLEs. MLE is very, very important for the all examination point of view. Is more weightage for nationwide universities. At least 5 to 10 marks here. Method of estimation. The weightage of the method of estimation is 5 to 10 marks. Remember this point here. So now thoroughly how to watch this video and understood the concept of the MLE and method of moments. Regularity conditions. Before applying the MLE, the following assumptions must be satisfied. First derivative and second derivative exist here. First derivative means dou log L by dou theta, either a partial differentiation or general differentiation. So now we can apply here dou log L by dou theta, dou square log L by dou theta exist and are continuous functions of theta. Must be continuous functions. Differentiable functions are continuous. Converse may not be true. So in the range R for almost all here. This is the first assumption. First assumption means here first derivative, second derivative must be exist. Definitely you have to apply the MLE concept. Third order derivative, dou cube log L by dou theta cube also exist. The range of integration independent of theta. This is very, very important. The range of integration is independent of theta. There is no lower limit and upper limit involving with theta here. So the range of integration is independent of theta here, but the lower limit value and upper limit value must be constant values. Properties are very, very important. Using these properties directly, you can able to write the MLEs of the given distributions. We have to find out the estimator of the unknown population parameter using different methods. Generally, we have three methods. One is MLE, other is a method of moments, and the least square method. MLE is very powerful technique. So now here, properties of MLEs. MLEs are always consistent estimators. So no need to take the consistent definition. First of all, you have to find out MLE. Identify the MLE, that is always consistent estimator. So don't bother about consistency conditions here. That lengthy process is there. Using MLE. MLE is there. Definitely that MLE is a consistent estimator. Directly can choose the answer. For a consistent estimator case, use this technique. MLEs are always consistent estimators. MLEs are need not be unbiased estimators. MLEs are need not be unbiased estimators. For each and every case, I am here is so I am giving one example here. MLEs are most efficient estimators. MLEs are most efficient estimate. The variance of MLE is less than the variance of any other statistic. So that's why MLEs are most efficient estimators. MLE, the variance of MLE estimator, ML estimator is less than the variance of any other estimator. That's why we can say that MLEs are most efficient estimator. If a sufficient statistics T for theta exists, I will give the complete detailed explanation in the next video. So now here is sufficient statistics T for theta exists. After that, the MLE will be a function of sufficient statistics. MLE will be a function of the sufficient statistics. Some cases, sufficient statistics same as the MLEs. Some situations, sufficient statistics exist. That is a function of MLE. MLE will be a function of sufficient statistics. It's very, very important property. MLE of a parameter need not be weak. I will give you one example. MLE for a parameter need not be weak. Very, very important bit. Direct bit for the examination point of view. Need not be unique. The distribution of MLE tests normally for large samples, asymptotically normal distribution. The distribution of MLE follows normal distribution. U comma sigma square. U comma asymptotically normal distribution. U comma sigma square. If MLE exists, it is the most efficient in the class of such estimation. MLE exists, it is the most efficient estimator in the class of such estimators. Several estimators are there, but MLE is the most efficient estimator. The variance of MLE is least compared to any other variance of any other statistic. So variance of MLE. So generally here MLEs are follows normal distribution. The sigma square value, variance of theta cap. Theta cap is called MLE. The variance of MLE is equal to 1 by minus n expectation of dou square by dou theta square log f of x comma theta. This is called I of theta. I will give the detailed explanation in the next videos. These are the very, very important properties. Several properties are there. Using these properties, easily we can solve the given problems. Remember this point. Invariance property of MLE is very important. Invariance property of consistency is already explained here in the last video. Now here is invariance property is very powerful property. Consistency and sufficiency has invariance property. Similarly, MLE also has invariance property. T is MLE of theta. Small t is MLE of theta. And g of theta is one-to-one function, is a continuous function. G of theta is a one-to-one function of theta. One-to-one function of theta. Then g of t is a MLE of g of theta. G of t is a MLE of g of theta. T is a MLE of theta. T square is MLE of theta square. Simply we can say that. T is MLE of theta. T square is a MLE of theta square. T is MLE of theta. Root 2 is MLE of root theta. Simply we can say that. Using this invariance property, so we can solve as many as problems. This very, very powerful property. Remember all students, this is a very, very important one. Examination point of view, so we have to apply these techniques. Easily we can write the results. So definition, regularity conditions, properties, and one more important property, invariance property explained. So now I am going to take some examples. Examples. For understanding purpose, first example, xi follows Poisson lambda, I is equal to 1 to and so on n, MLE of lambda dash. Step 1, construct the likelihood function. The likelihood function is equal to product of the marginals. Is a directly joint function. Here is n samples are there. I is equal to 1 to n. P of xi comma lambda. Probability mass function. Phi I is equal to 1 to n. E power minus lambda. Lambda power xi by xi factorial. That is equal to e power minus lambda constant. Here is taken outside n times n lambda. So lambda power x1, lambda power x2 by expansion, lambda power xn dividing by I xi factorial. I is equal to 1 to n. Pi xi factorial is a purely constant term. L is equal to e power minus n lambda base equal powers adding summation xi by k. K is what here? Constant value. K includes k is equal to pi xi factorial. Our convenience, we have to take this one. So next, apply the logarithm both sides. Log L is equal to minus n lambda log e base e plus summation xi log L. Log a power m is equal to m log e minus log k. Now, apply the principle of maxima minima technique. Here is differentiate one with respect to lambda. Dou log L by dou lambda is equal to 0 implies minus n with respect lambda is 1. Log e base is 1 here. Summation xi is a constant value. So next to differentiation of log L is 1 by lambda Differentiation of constant is 0 and equating to 0. Now, minus n plus summation xi by lambda is equal to 0 implies summation xi by lambda is equal to n. So lambda cap is equal to summation xi by n, that is equal to x bar. No need to take the second derivative here, directly the concept dou square log L by dou lambda square definitely less than 0 at lambda is equal to x bar. Find second derivative of 1, differentiate 1 with respect to lambda twice and substitute lambda is equal to x bar, definitely this value negative. Therefore, here MLE of lambda is equal to x bar. So this MLE of lambda x bar is a need not be unbiased estimator. MLE of lambda is a consistent estimator, is a most efficient estimator. So sufficient stats exist, it is a function of MLE. So now, so here is using this MLE, you can also answer the 2 or more questions here. So MLE is very, very powerful. This MLE of lambda follows normal distribution, x bar follows normal distribution, mu commas sigma square by n. So this is a very, very important technique to estimate the unknown population parameter. Next, second example. Example 2. Example 2. Xi follows Bernoulli 1 comma theta, I is equal to 1 to n, and so on n. Probability mass function of xi is equal to probability mass function of xi equal to P of xi is equal to theta power xi 1 minus theta whole power 1 minus xi. Xi takes values 0, 1. IIDs likelihood function equal to pi. I is equal to 1 to n. N samples are drawn. P of xi comma theta, that is equal to pi. I is equal to 1 to n theta power xi 1 minus theta whole power 1 minus xi. Now here expansion theta power x1 1 minus theta whole power 1 minus x1 theta power x2 1 minus theta whole power 1 minus x2 and so on theta power xn 1 minus theta whole power 1 minus xn. Now L is equal to base equal powers adding theta power summation xi 1 minus theta whole power n minus summation xi. Now immediately you have to apply the logarithm both sides. Take logarithm both sides. Log L is equal to summation xi into log theta plus n minus summation xi log 1 minus theta. Now this is equation 1. To get MLE of theta, differentiate 1 with respect theta, we get dou log L by dou theta is equal to 0 implies summation xi log differentiation of log theta is 1 by theta plus n minus summation xi constant differentiation of log 1 minus theta 1 by 1 minus theta again differentiation of 1 minus theta bracket function, that is minus 1 equal to 0. Summation xi by theta plus into minus minus n minus summation xi by 1 minus theta is equal to 0. Implies summation xi by theta is equal to n minus summation xi by 1 minus theta. By cross multiplication, summation xi into 1 minus theta is equal to n minus summation xi into theta by cross multiplication. Multiply with 1, summation xi minus theta into summation xi is equal to n theta minus summation xi into theta. In left side, right side, summation theta, summation xi into theta, summation xi into theta cancel. Remaining part, summation xi, I is equal to 1 to n is equal to n theta. Implies theta is equal to summation xi, I is equal to 1 to n by n. Now, therefore, theta is equal to x bar. Theta is equal to x bar. MLE of theta is equal to x bar. Automatically here second derivative, no need to take second derivative. Dou square log L by dou theta square less than 0 at theta cap is equal to x bar. Theta cap estimator MLE of theta is x bar for Bernoulli population. Is very, very important one. Example 3. As follows. Exponential parameter theta xi follows. Let x1, x2, xn be a random sample drawn from this exponential population with parameter theta. I is equal to 1, 2, 3 and so on n. MLE of theta dash. Here is the PDF of x is xi is f of xi is equal to theta into e power minus theta xi greater than or equal to 0. There is a PDF of exponential distribution. Now, the likelihood function pi I is equal to 1 to n f of xi comma theta, that is equal to pi I is equal to 1 to n theta into e power minus theta xi. Now, here is pi I is equal to 1 to n theta e power minus theta xi. Now, expansion theta into e power minus theta x1, substitute I is equal to 1. Next, pi means product values, theta e power minus theta x2 and so on theta e power minus theta xn. L is equal to theta into theta n times theta power n e power minus theta x1 minus theta x2 base equal powers adding theta xn. L is equal to theta power n e power minus theta is taken outside is a constant value x1 plus x2 plus and so on xn, that is equal to next one L is equal to theta power n e power minus theta summation xi. Now apply logarithm both sides. Log L is equal to n log theta minus theta summation xi log e base e. Here we are using base e logarithm functions. So both sides apply the log base e. Log L is equal to n log theta minus theta summation xi. This is equation 1. To get MLE of theta, differentiate 1 with respect to theta, we get now dou log L by dou theta is equal to 0 implies n by theta minus, with differentiation with respect to theta, here we get summation xi is equal to 0. Summation xi is equal to n by theta. So theta cap is equal to n by summation xi. This is 1 by x bar. 1 by x bar. So dou square log L by dou theta square less than 0 at theta cap is equal to 1 by x bar. Therefore, MLE of theta is equal to 1 by x bar of exponential distribution. It's very, very important from the examination point of view. One more example. X follows, xi follows. Normal distribution is very, very important one. Mu comma sigma square. There are two parameters. Two parameters are unknown. We have to find out MLE of mu and sigma square. There are three cases here. Mu is unknown, estimate mu. Sigma square is unknown, estimate sigma square. Both are unknown, estimate mu and sigma square. I is equal to 1 to n MLE of mu and sigma square. First, here is PDF of x. Normal distribution PDF. 1 by sigma root 2 pi e power minus half x minus mu by sigma whole square minus infinity to plus infinity. Case 1. Mu is unknown and sigma square is known case. Known case. To find MLE of mu. To find MLE of mu. Now, likelihood function. Likelihood function is common for both mu and sigma square here. Pi is equal to 1 to n f of xi comma mu comma sigma square. Pi I is equal to 1 to n 1 by sigma root 2 pi e power minus half xi minus mu by sigma whole square. Now, here is apply the pi 1 by sigma root 2 pi whole power n e power minus half summation base equal powers adding summation I is equal to 1 to n xi minus mu by sigma whole square. Apply the logarithm both sides. Log L is equal to n into log of 1 by sigma root 2 pi minus half into summation I is equal to 1 to n xi minus mu by sigma whole square. Log E base E. Sigma is a known value, constant value is taken outside. Log L is equal to n into, this totally is constant value. Sigma known value, root 2 pi is what? This is constant value. This is completely constant. Log K. K is called 1 by sigma root 2 pi. Minus half summation I is equal to 1 to n Here is sigma is a constant taken outside. Sigma square here. Whole square is there. Xi minus mu whole square. Log E base is 1. Now this is equation 1. Differentiate 1 with respect mu first here. We get here is sigma square is a known value, constant value. Here differentiation of 1 with respect mu we get dou log L by dou mu is equal to 0, implies differentiation of constant is 0, minus 1 by 2 sigma square constant. Now here is treating as x square. Differentiation of x square is 2x. 2 into summation I is equal to 1 to n xi minus mu. So again differentiation of bracket function. Xi is a constant value, mu is a variable. Differentiation of mu is 1. Here is constant value 0, 0 minus 1, minus 1, equating to 0. Now here minus minus is plus, 2 cancel here. The remaining part 1 by sigma square summation I is equal to 1 to n xi minus mu is equal to 0, implies sigma square is always positive, cannot be 0. Sigma square greater than 0. So now here the numerator value must be 0. Summation I is equal to 1 to n xi minus mu is equal to 0. Now apply the summation. Summation I is equal to 1 to n xi minus summation I is equal to 1 to n mu is equal to 0, implies, so now summation xi I is equal to 1 to n is equal to summation I is equal to 1 to n mu. Summation xi is called nx bar. Summation mu is called n mu, implies nn cancel. So mu cap is equal to x bar. So therefore MLE of mu x bar when sigma square is known value is very, very important. Sigma square is known value. So this is a procedure to find the MLE of mu for normal distribution. It's very, very important. Next to case 2. Case 2. Sigma square is unknown and mu is known value. Mu is known. To find MLE of sigma square. The likelihood function here is from this one log L. Here is before equation 1 log L is equal to, apply this logarithm, log L is equal to log of 1 by sigma root 2 pi. There is n into minus half 1 by 2 sigma square summation I is equal to 1 to n xi minus mu whole square. Now here is sigma is a variable. Now log L is equal to n log a by b, log 1 minus log sigma root 2 pi minus 1 by 2 sigma square summation I is equal to 1 to n xi minus mu whole square. log L is equal to log 1 is 0 minus n log sigma minus n is a common factor. Log a into b, log a plus log b, log root 2 pi minus 1 by 2 sigma square summation I is equal to 1 to n xi minus mu whole square. So here we have to find the MLE of sigma square. Here is sigma is there. Now convert the sigma is into sigma square. In this case, apply the logarithmic properties. So now this is purely constant value minus n by 2 log sigma square. Log a power m is equal to m log a. So log a power m is equal to m log a. So 2 into log sigma. 2 cancel, there is no change here. So this is purely constant value, is k. Minus n log root 2 pi is a purely constant value, treating as a k. Minus 1 by 2 sigma square summation I is equal to 1 to n xi minus mu whole square. Now this is equation 1. Differentiate 1 with respect sigma square, we get dou log L by dou sigma square, dou log L by dou sigma square. So sigma square is a variable equal to 0 with respect sigma square. So now minus n by 2 constant. So this is treating as a x. Log x is what? 1 by x. X means sigma square. Is treating as x here. Differentiation of constant is 0 minus, this is purely constant, summation I is equal to 1 to n xi minus mu whole square. Here is 1 by 2. Here is 1 by sigma square. 1 by sigma square means 1 by x. Differentiation of 1 by x is what? Differentiation of 1 by x minus 1 by x square. That is x is called sigma square whole square, equating to 0. Now minus n by 2 sigma square. Here is 0. Here is minus plus plus 1 by 2 sigma square whole square into summation I is equal to 1 to n xi minus mu whole square equal to 0. Now bringing to this is the right side, or here is right side, 1 by 2 sigma square whole square summation I is equal to 1 to n xi minus mu whole square is equal to n by 2 sigma square. Now cancellation. 2 cancel. Sigma square, 1 sigma square cancel. Now our requirement, sigma square cap is equal to, by cross multiplication, summation I is equal to 1 to n xi minus mu whole square dividing by n. Therefore, MLE of sigma square is equal to 1 by n summation I is equal to 1 to n xi minus mu whole square. Here mu is known case, constant. Note, if mu is unknown, use x bar, because x bar is a unbiased estimator or MLE of mu. In this case, then MLE of sigma square equal to 1 by n summation I is equal to 1 to n xi minus x bar whole square. This is same as to small s square. Remember here, MLE of sigma square is equal to small s square. Sample variance. So expectation of s square not equal to sigma square. MLEs are need not be unbiased estimators. This is example. MLEs are need not be unbiased estimators. It's very important example. So for normal distribution, MLE of Q, MLE of sigma square obtained. So one more example, example 5. Xi follows uniform distribution 0, comma theta. I is equal to 1, 2 and so on n. MLE of theta dash solution. Now the PDF of f of x equal to 1 by theta. 0 less than or equal to x less than or equal to theta. As usual procedure. Likelihood function phi I is equal to 1 to n. F of xi comma theta. Phi I is equal to 1 to n. 1 by theta. That is equal to 1 by theta power n. Take log both sides. Log L is equal to log of 1 by theta power n. That is minus log theta power n. Apply log a power m concept. Minus n log theta. This is equation 1. Differentiate 1 with respect theta. We get dou log L by dou theta is equal to 0 implies minus n by theta is equal to 0. From this one, theta cap is equal to infinity. Clearly, it is observed value. Observed result. Observed result. In this case, we locate MLE as follows. So we have to choose theta so that L is maximum. L is maximum. We have to choose the theta so that L is maximum. So now here is L is equal to 1 by theta power n. So when this L is maximum, when theta is minimum. In this case, we have to use order statistics technique. Order statistic technique. Order statistic. That x1, x2, xn be a random sample drawn from this population. Continuous uniform distribution. x1 order less than or equal to x2 order less than or equal to and so on less than or equal to xn order. Now this sequence lie between 0 to theta. 0 less than x1 order less than or equal to x2 order less than or equal to xn order less than theta less than or equal to also. Here is 0 including here. Now in this sequence, in this ascending order, the minimum value of theta is what here? Xn order, the minimum value of theta. The least value. Theta is greater than or equal to xn order. The least value of theta is xn order. This is the minimum value. So L is maximum if theta is minimum. Theta is minimum. The minimum value of theta is xn order. Xn order means here xn order is the maximum of xis. So therefore, MLE of theta is equal to xn order. Xn order. So this is the actual procedure, but we have to apply thumb rule. Alternative method is there. The given PDF f of x equal to 1 by theta 0 less than or equal to x less than or equal to theta. The range of the x depends on parameter theta. Use order statistics method. Here in this interval, the theta falls right side of the x. When theta falls right side of the x, so the minimum value of theta is xn order. When theta falls left side, the maximum value of theta is x1 order. Depends upon these two, we can able to write the MLEs. Once again, here using thumb rule, the range of the random variable x depends on parameter theta. The theta may be falls in left side or right side. The theta falls in right side. The minimum value of theta is xn order is MLE of our parameter theta. The theta falls in left side. X1 order is a least observation. X1 order is a maximum value of theta. That is MLE of the parameter theta. I am giving the two or more examples for understanding purpose. But in this case here, 0 less than or equal to x1 order less than or equal to x2 order less than or equal to and so on less than or equal to xn order less than or equal to theta. Therefore, theta is right side. Theta is greater than or equal to xn order. So simply we can say that definitely MLE of theta is equal to xn order. So using simple technique here, our aim is L is maximum. L is maximum means L is a function of theta, 1 by theta whole power n. So when the L is maximum, theta is minimum. The minimum value of theta in this sequence is xn order. Xn order is what here? Maximum of value of xi here. That is the minimum value of theta. Substituting this value, definitely automatically L is maximum. Using this technique, easily we can find out the MLEs of unknown population parameter theta. One more example. Xi follows uniform alpha comma beta. I is equal to 1 to n. Here, jointly we have to find out MLE of alpha and beta. Now, using the simple technique, this is the Saxena technique, HC Saxena technique. F of x I is equal to the PDF of uniform distribution is beta minus alpha, alpha less than or equal to x less than or equal to beta. Here we have to give the jointly MLEs of alpha and beta. Alpha is the left side of x and beta is the right side of x. So now the order statistics, alpha less than or equal to x1 order less than or equal to x2 order less than or equal to, and so on, less than or equal to xn order less than or equal to beta. So now the likelihood function is 1 by beta minus alpha whole power n. So L is maximum whole power n, not 2. L is maximum. Here we have to choose the alpha and beta values. So alpha is the left of x, beta is the right of x. Therefore, so alpha cap is equal to the minimum, the maximum value of alpha is x1 order. That is equal to minimum sample observation, minimum xi. Beta cap is equal to xn order. That is the minimum value of beta is equal to xn order. This is the maximum of xi. Maximum of xi. Now, by substituting these two in this one, L is maximum. L is maximum. L is maximum if beta minus alpha is minimum. How to get this beta minus alpha is minimum here? So now here, so beta is xn order, beta alpha is x1 order. Xn order is the largest sample observation. Largest sample observation in the collected sample. X1 order is the smallest value. The difference of this gives minimum value. If beta takes the minimum possible value, takes the minimum possible value, and alpha takes the maximum possible value. In this situation, the difference is minimum, automatically L is maximum. Therefore, MLE of alpha is x1 order, MLE of beta is xn order. Joint estimators x1 order, xn order. So this is a very, very important problem for the examination point of view. Easily we can solve this problem using the HC Saxena shortcut method. The range of the x depends upon parameter theta. Definitely you have to apply the order statistics technique, HC Saxena shortcut method. Apply this method and to obtain the MLEs of unknown population parameters. Problem 7. let x1, x2, and so on xn be a random sample from rectangular distribution. PDF is given f of x equal to 1 by 2 theta minus theta less than or equal to less than or equal to plus theta. Theta is always greater than 0, equal to 0 otherwise. Now, the likelihood function L is equal to phi, I is equal to 1 to n, f of xi comma theta, phi, I is equal to 1 to n, 1 by 2 theta, that is equal to 1 by 2 theta whole power n, whole power n. Here the range of x depends on theta. So minus theta less than or equal to x less than or equal to theta. This implies mod x. This can be taken as mod x less than or equal to theta. Now order statistics. Mod x1 order less than or equal to mod x2 order less than or equal to, and so on, less than or equal to mod xn order less than or equal to theta. L is maximum if theta is minimum. Theta is minimum. The minimum value of theta is modulus xn order. Modulus xn order. Or maximum of max of mod xi. Therefore, MLE of theta is equal to max mod of xi. So this is very, very important for the examination point of view. Here, remark for generalization case. X follows uniform a minus theta. X follows uniform a minus theta comma a plus theta. Continuous uniform distribution. A is known value. Theta is greater than a is arbitrary constant known value. Any known value, constant value. In this case, MLE of theta is equal to same as above here. Maximum of xi modulus of xi minus a. You can apply this technique for any arbitrary point a. So 2 minus theta, 2 plus theta. The result is maximum of mod of xi minus 2. It's very simple one. Remark is very, very important. One more example. 8, problem 8. Let x1, x2, and so on xn be a random sample drawn from the population with PDF f of x equal to e power minus of x minus theta, x greater than theta, x greater than equal to theta. X greater than equal to theta. Now here is L is equal to I is equal to 1 to n e power minus x minus theta xi. So now this is equal to e power minus summation I is equal to 1 to n xi minus theta. L is maximum if theta is maximum. Theta is maximum. Here theta value is maximum value. Definitely L is also maximum. The exponential function is there. Now, using order statistics technique, the theta less than or equal to x1 order less than or equal to x2 order less than or equal to xn order. The maximum value of theta is x1 order, that is equal to minimum of xi using shortcut method. Therefore, MLE of theta is x1 order. MLE of theta is x1 order. It's very, very important problem. Next problem, one more example, problem 9. Let x1, x2, and so on xn be IAD random variables having IAD random variables having Laplace density f of x equal to 1 by 2 e power minus modulus x minus theta. The limits are minus infinity to plus infinity. Here, in this case, likelihood function I is equal to 1 to n f of xi comma theta. I is equal to 1 to n 1 by 2 e power minus modulus xi minus theta. That L is equal to 1 by 2 whole power n e power minus summation xi I is equal to 1 to n modulus xi minus theta. L is maximum. Our aim is L is maximum. When theta is minimum value, because of modulus is there. Because of, see the difference of the previous problem and this problem. L is maximum and theta is minimum value. So we have a concept in descriptive statistics. Summation I is equal to 1 to n modulus xi minus modulus xi minus theta is minimum if theta is median. Theta is median. Theta is median. Summation modulus xi minus theta is minimum. Therefore, MLE of theta is sample median. MLE of theta is sample median. So this is a very, very important problem for the examination point of view. So this summation xi. So we have a concept. Sum of deviations taken from absolute deviations taken from median is always minimum. Summation modulus xi minus median is always least. Always least. This is a very, very important one. MLE concept explained, definitions, properties, regulatory conditions, important properties are given. A few examples are noted here. All these examples are very, very important for the examination point of view. You can able to solve the remaining problems using this knowledge. Thank you.